10:30, 10:31, so good time to start. So welcome everybody. Interesting morning trying to get that back up and working. So, okay, so the topic that we're going to talk to today is, so you found PD, what next? And we're going to share some of the wisdom that myself and Brad have sort of gained over the last so many years of doing PD testing non-intrusively. So the main focus, or the overall content of the presentation today, will very briefly introduce condition monitoring and partial discharge. We will be assuming that everybody's relatively familiar with it at this point. And then we'll talk about the handheld PD detection. I'll go through ultrasonic testing and the results that we get from that. Brad will then take over and talk through transient earth voltage, electromagnetic measurements, and the results. Through the presentation, we'll have case studies. Brad will also finish on one interesting one at the end, and then we'll just summarize it. Any questions at any time, feel free to shoot them through as we're going through. If we can take them as they come, we will. If not, we'll certainly mop up at the end and make sure that we've answered all the queries on that. Okay. So just very briefly on condition monitoring and partial discharge. The reasons generally that we're doing condition monitoring on our switchgear, on our cables, or basically all our HV assets is threefold really. Generally, we're looking for increasing safety. So we're looking to prevent failures happening in the substation, improve the safety of us working in there. If we've got, if we're preventing failures, we're obviously looking at also improving the asset performance. So prevention of the failures, prevent the outages, looking after our SAFEs, customer minutes lost, customer interruptions, whichever way you want to talk about it. And on top of that, we know that if we can intervene and we can take a problematic asset off the network before it fails, that is going to give us a financial benefit. So fixing before fail is going to give us a significant benefit financially, as well as in the performance of the asset. So all three of those are very much interlinked. Where do we get failures? Well, we get failures on new style switchgear. We get failures on old type switchgear as well. Age is not the 100%. It's not just an age-based factor. If we see the two pictures that we've got, problems that we found here, we've got the internal arc rated bus bar that we've got some surface tracking that's caused us a failure in that bus there. Now hopefully with the internal arc rated nature of that switchgear, we've got limited, or we've got lesser safety impact than that, but we're still going to get the outage, unexpected outage that's going to cause us network problems. The picture on the right hand side is a bitumen filled cable box that is blown up. Again, we've got the outage problem. The additional impact here is the disruptive explosion. So you can see how much of the explosion debris has gone onto the wall there. If we're in the substation at that time, the time that the disruptive failure, then of course we've got much more chance of a problem and a safety incident. When we look at the statistics of what causes us disruptive failures, the unexpected disruptive failures in substations, then we're looking around 80 to 85% of disruptive failures have partial discharge or are caused by partial discharge before we get that bang occurring. So that's why we do condition monitoring and partial discharge testing. Very briefly on the classifications of PD, there's three main types of PD that we look for. The first two are the most onerous and the ones that we specifically target in switchgear in particular. That's the stuff that's happening internal to insulation, so something that's happening deep inside the solid insulation. The difficulty with that one is you're not going to get any warning by visual examination. You're never going to be able to hear or smell the discharge byproducts when you've got a problem deep inside that. So the compound insulated cable box that had blown up on the previous slide, first warning you would have had is that it disruptively fails. So no prior warning before we get that explosion occurring, and that's due to an internal type discharge. When something is happening across the surface of the installation, so much like in that bus bar situation, you do get a potential chance, obviously with a visual examination of the bus bar, you can potentially see it. But you also get some byproducts, nitrous oxides and ozones. The smell can permeate from the switchgear, and that can give you earlier warning on that. However, with modern, more air insulated switchgear you get a bigger chance of surface discharge happening through on air insulated components. The third type of discharge is corona discharge. We see this more on a sharp point into a gas, and often you'll get that in the open terminal switch yards. Not a massive issue unless you have the corona discharge happening inside, say, an air insulated chamber which is enclosed, and then what happens is the byproducts, nitrous oxides, generate the nitric acid and start attacking the insulation and then making surface discharge happen on that switchgear. So the two that we particularly concentrate on are internal discharge and surface discharge. Next slide. So in order to detect these different types of discharges, we use different techniques. So for the internal discharge, or for internal discharge and high levels discharge, surface discharge worth, we use the capacitive probe and the transient earth voltage detection method, which Brad will talk to later. For surface discharge, we tend to have a much lower amplitude of discharge, but a different type of breakdown of the insulation, and that is more readily detected using the ultrasonic technique, which I'll talk through in the next few slides. When we start going further into the investigation of discharges, or we're looking for discharges down cables, then we can add in different sensors, the HFCT or RFCT, to use for that. When we work in open terminal switch yards in particular, or where we can't actually use a TEV probe because we can't touch any earth metalwork, then we often go into the UHF directional antennas. We're not really going to cover the RFCT and the UHF in this particular presentation today. We can cover that on a future webinar. So let's look at handheld PD detection using the UltraTEV Plus2. And I'll concentrate now just on the ultrasonic measurements. So ultrasonic measurements, when we're carrying out ultrasonic testing, we're looking to, we're trying to detect something that's happening on the surface of that insulation, the sort of sound that we can eventually hear when things degrade to the level that you can audibly hear discharge inside the switchgear and in your substation. The most sensitive sensor that we use for detection of ultrasonic is the airborne microphone sensor. So that's the most sensitive, and that's the one you should use by default. What you're doing is you're moving the microphone and you're pointing the microphone towards the gaps in the metalwork. So you're scanning around the voltage transformers and maybe up towards the circuit breaker spouts on rackable switchgear, the cable boxes, bus bar vents, things like that. So on that first one in the bus bar failure, the way to have tested that would have been in the sort of blast vents at the top where the bus bar chamber is. This particular picture you can see here, we're measuring and we're pointing the ultrasonic microphone in the gaps around where the cable box is on this spring main unit. Quite coincidentally, there's an arrow pointing down to that exact same spot where we did find discharge as well. So manufacturer is a bit very good at very helpful in that.
They pointed it out.
They pointed it out before we even got there, which is great. Now you can also use a contact probe. So we do get situations where people are talking about using contact probes as the primary tool rather than a sort of secondary tool. We would always tend to use that as a secondary sensor. So if we've got any air insulation, any air gaps into our chamber, then there's no massive benefit in using the contact probe. You can use it, but the airborne probe is your classic, or is your optimal sensor. In the middle here, we've got a completely sealed chamber, and that's exactly where your contact probe should be used. If you do have stickers, any danger of death type stickers, notices, or something on the switchgear, then use that to enhance the coupling, and that's where the contact probe really comes into its own. If you've got double skin switchgear, then generally you're not going to get the signals that will enable your contact probe to detect anything. So that double skin switchgear becomes very problematic. In all honesty, we've gone to many sites where it says, you know, people have said that you can't actually take ultrasonic because it's double skin switchgear and you won't get any air gaps at all. And we've never found that to be absolutely 100% true. So there is usually some sort of air gap in towards most chambers on switchgear if you just look hard enough. So the contact probe is a really good sensor, but it's the secondary sensor. Use it only when needed. We do tend to use the airborne probe and then just the contact probe as a backup for us. So an overall very quick summary of how we do ultrasonic testing is we test everything. We test all the chambers. We're listening for differences along the switchboard. We're listening for that distinctive crackle sound, the sort of, you know, the frying pan sort of sound that you get from PD. When you're using the instrument, I'm going to go through that we check the phase plot and we check the algorithm to give us better interpretation. But in reality, when you're taking the testing, when you're doing the testing, concentrate on the listening. Don't concentrate on the screen. When you hear something, then use the screen to give you that additional interpretation and everything else. So fully focus on placing your sensor nice and gently around all the air gaps and listening for something that is different. The majority of the time that you're going to be testing, you're going to be hearing nothing. You'll just hear a very small white noise in there. When it's present, that's when we take a reading. So we record the instance of partial discharge on the instrument when we hear something. We don't generally take a reading on every single panel like we do with TEV. Surface discharge. That's a new one.
Haven't heard it called that before.
No, but surface PD, it won't go away. It will always get worse. It will. It's a cumulative effect as it degrades. So once you've got it, really, we need to start investigating that. Yeah. Okay, so when you're taking the measurement, like I say, you're listening. Listening is the most important thing. You do get the screen which shows you the amplitude, the number. So once you've found a PD, we hold the microphone in at the highest level where we can listen to it most, and we take a reading. So you can see 25 dB on this particular one. The color chart at the bottom gives us a phase resolve plot of the partial discharge, and it's an intensity plot. So you can see where things are happening in relation to the 50 or 60 hertz cycle. So you can see in this particular instance here, we've got some clusters which are phase locked, and we'll show again some more examples of what that means in the next coming slides. The additional thing that you have to help you here is a classification algorithm where it says partial discharge or noise. This is where the instrument will make an assessment of what you're listening to. So it helps the less experienced users to make a judgment call of whether we're detecting noise or PD. Always trust your own self, but what we tend to do is we listen, we make our own judgment call, and we use that algorithm as sort of a sense check backup and to give us, particularly on the 50-50 calls, to give us additional confidence, really. So the algorithm is really, really valuable, particularly when you're just starting out on that. So you can see on this particular screen here, we've got two different screenshots. The one on the left-hand side it's a phase lock pattern that we've got underneath there, but it's 21 decibels, so it's quite high, but it's being classified by the instrument as a noise source, not a PD source. The one on the right-hand side, again clustering, but this time similar sort of levels, 29 decibels, but being classified as partial discharge source. So that's a useful guideline to help you in the interpretation. Okay, wrong button. So an example for you of what you may find. So in this particular slide here, we've got rackable voltage transformers on some 11 kV switchgear. In the particular board that we're testing, we found two sources of ultrasonic activity on two voltage transformers, just 2 panels away from each other. You can see the top one there, we've got a phase resolve plot which is locked to the sine wave, but is a relatively, it's sort of stochastic, it's sort of random around the same spots. We've got two significant clusters 180 degrees apart from each other, and there's sort of a random nature. If we play the sound, you should be able to hear the noise that we get from that as well. Okay, so it's quite an aggressive crackling sort of sound. If it sounds aggressive, it sounds nasty, it usually is. That's a pretty basic rule that we go for ourselves there. So that one is classifying as PD. It looks, the clustering looks like PD and it sounds like PD to us. The one on the bottom, on the other hand, is classifying as 100% certainty or 100% classification of noise, and that sounds like this. So with that one, it's more of a mechanical sort of magnetic type noise. So the sort of thing that you're almost saying, yeah, it sounds like transformer noise. It's again phase lock though. If you look at the patterns that we've got on the on that phase lock, you'll see there are some very tight clusters on there. So you've got some very dark spots, but they are really tight. So when we see these very tight clustering, that's almost something that's happening in a machine type way. You see the same thing on rotating plant where you see very vertical clusters at the exact same spot, exact same point on the wave every single cycle. That's not generally how surface PD will occur. What surface PD will be more of a random nature around the rise and the fall of the 50 hertz, 60 hertz cycle. So that's why we get that more random effect that we see in the top picture.
Just got one question here, Neil, from James Fry. What would the VT PRPD pattern look like if it weren't phase locked?
If you didn't, right. So if you didn't achieve a phase lock, yep. Okay. So if you didn't achieve a phase lock using the instrument on the opto sensor to lights, then what you could actually do in both of these instances is you can manually adjust the phase lock so that you still achieve these two patterns. So what you'll find is if you're off. If your frequency is off, you'll see things drifting across the screen, left to right or right to left, depending on if you're above or below the frequency, the optimal frequency. And you'll see things drifting, and then you'll end up with a whole mush across the screen, so flat lines. So what you do is you place the instrument into a manual mode, and you adjust the frequency that the instrument is capturing at until you start seeing the clusters appearing. So it is absolutely possible, even if you haven't got reference to a light source to give you that optimal, that phase lock, is to adjust it and see these clusters occurring. If it's completely random and it's just appearing across the screen very quickly, and you're not seeing any drift left to right, right to left, then that is a genuine noise type source. So you will see some noise sources ultrasonically where it is just flat across the screen from almost the moment that you take the measurement. If you're seeing the drifting, then you have got a phase lock. You can manually adjust and you can still achieve these two things here. Quite interestingly, you can get quite a lot of phase lock stuff from things such as fluorescent lights, which are are pumping out PD, things like that. That generally also gives you the phase lock, mind you. So there is phase lock noise in the ultrasonic that you will find ultrasonically. The good thing about ultrasonic as well is it's very, very directional. So if I'm pointing in towards this VT, I know it's coming generally from the VT. If I've got an interference source from a light bulb or something above me, then the highest signal is coming from there. So that also helps you determine that it is noise source or a genuine PD. This particular instance here, both found pointing towards the gap between the fixed moving portion of the VT, but the phase lock, the phase pattern, and the noise characteristic tells us that one is PD and one isn't. So what does the PRPD plot tell me? And it can tell me quite a lot of things nowadays. So we can see the difference between different types of discharge, and we can then start using that to look at what are we going to open up, what we're going to try and see. So the top left one here is a corona discharge that occurs on one half of the cycle only. So we see a single cluster. The top right is a single phase discharge. There's two clusters, 180 degrees apart, and they're relatively sharp. So the off period is generally longer than the on period on the plot across the 360 here. That gives us a good indication that we've got a single phase type discharge happening. Multiple phase discharge in the bottom right, mind you, we've got a longer period of the high level on, and that's the sort of discharge that we see when we've maybe got phase-to-phase discharge on a cable termination overhead underground, which inside the cable box. This particular one here was from an overhead cable termination where the spacing wasn't adequate, and we could see that we get interference between different phases. When we get a contact type problem, so something is not quite making, there's a floating metalwork, I think Brad will also show this on TEV later, we get these long flat clusters that we see here. We do get them happening quite a long way across the cycle. There will be these dead points in this particular instance here, you can see it, and we do see it sort of not being quite as flat towards the end of the that cluster. On the TEV, it tends to stay a much flatter shape than that, but that gives us an indication. So when we get this PRPD, we can then start looking at, is it a problem? Do I need to go in? What sort of defect am I going to look for? Okay, so the next slide will show you an example of how we use that to interpret. So we've opened up, we've had the phase plot, as you can see here. It's quite a large clustering, so it's happening for quite a long period of time. So that gives us an indication that, again, there's more than maybe one phase involved. Sound sounds like PD. It's that crackling sound again. The algorithm in that particular case indicated 97% certainty of PD, and when we opened it up, lo and behold, what we've got here is the voltage, the HP leads off the VT are too long. So what we're getting them is looping around towards the earth on the red and the blue phases here. So we can see we're getting discharge interference between the HV lead on the voltage transformer on two phases, hence the pattern that we're seeing in our phase resolve plot there. So that gives us an indication we've got two. We go in there, we see two, we fix it up. A relatively easy fix, and something that the quicker you do it, the easier the fix, and less time you're going to have to spend rectifying that, taking it off the system. So what does the number mean? This is the difficult one. So we found a discharge and we've got 26 dB, we've got 21 dB. Then we have to start making an assessment of what that means, and that is the most difficult thing when it comes to ultrasonic type testing. If we look in this particular slide here, we've got, this is some lab type work that we did a few years ago, and you've got two different measures of discharge that were taken 20 minutes apart from each other, and one of them is 75 times higher in amplitude than the other. So the one on the right hand side, significantly higher levels of of surface discharge occurring, significant more noise in the ultrasonic mode, and so significantly higher picocoulombs, but only around 250 picocoulombs. The one on the left, 35 picocoulombs, so about 75 times higher. However, they're taken within 20 minutes of each other. If we were to open that up and see the level of insulation that we've got left, it's in exactly the same deteriorated state. The only thing that has changed is the level of humidity in the atmosphere in that test chamber. So making an assessment of the number based purely on one spot measurement, and it is not really a very relevant thing to think, you know, how serious it is, because you actually, you know, like I'm saying, 75% more with the same level of degradation just because of the humidity. So the discharge itself and the level of degradation is not dictating the amplitude. On top of that, you've got things such as, if you've only got a small air gap, you're only going to get small amounts of sound out. Barriers will block the transfer of waves. So overall, putting an assessment of the level of the seriousness of ultrasonic testing just by the number is a very, very difficult thing, and probably an erroneous thing to do. Further work that we've got here, we took an 11 kV circuit breaker all the way through to failure. We've got a couple of plots here. They're very degraded. The top one, we've got maybe about 50 millimeters of insulation left before it fails. The bottom one, we've got about 3 or 4 millimeters of insulation left. The level of discharge in both cases, almost exactly the same. We took the circuit breaker through to failure in a controlled environment, and there was no positive upward trend as we ove towards failure. So again, trending ultrasonic, not necessarily something that can be done and provide you confidence that things are getting worse or not getting worse. The only time you know that things are not getting worse is if you can reduce it all the way back to no discharge at that point in time by maybe controlling the environment. So this is an example to show you on that. This is a failed circuit breaker, or a circuit breaker that was monitored all the way through to failure in the field. So they didn't actually want it to fail, but it did anyway. And what we've got here is a level of discharge that rose all the way up to about 40 dB, which is very loud, but at the same time there was a really good air path towards the circuit breaker spouts in this particular instance. So you're going to get large signals. And then you can see it stayed around the same sort of level for about 3 or 4 months, and then it disruptively failed. So there's no positive upward trend as we move towards failure. So ultrasonic sort of testing and surface discharge as a phenomenon means that it's actually pretty difficult to try and grade it and to trend it. So for interpretation, to summarize what we do in that, really, the absolute number is not the primary consideration. When we're testing, the more important thing that we concentrate on is, does it sound like PD? What's the characteristic? What's the algorithm saying? Is it discharge? Is it genuine discharge? If it's genuine discharge and it's coming from within the switchgear, the only surefire way of understanding the level of degradation is to take an outage and carry out a visual examination. That will tell you how long you've got left. So in this particular instance, we've taken an outage and we can see what we've got a problem here. We're going to have to replace that cable termination just because of the sloppy nature of leaving large earth leads in the wrong place here. Previously, it was a lot of just user experience. Does it sound like discharge? Nowadays, with the PRPD and the algorithms, that helps us interpret, is it single phase, is it multiple phase, and also what type of discharge we look for, and the positivity of, is it PD or is it noise? So that's how we trace things through on an ultrasonic level. And Brad, once he's finished typing some of the answers to the questions, is going to take us through TEV measurements.
All right.
Do you want to swap?
We can, yeah. Everyone's shooting a fair few questions through, so it's been really good. I've answered a fair few. Some people are putting the questions in the questions. Other people are putting them in the chat. So we're getting a fair few coming from everywhere, which is good. Okay, I'm going to cover TEV measurements, TEV results. So Neil covered ultrasonic. I'll cover TEV. I'll do that now. Oop, double clicked. Go back a slide. Okay, the TEV survey technique. So TEV signals are detected on the surface of switchgear and on the surface of cables. So you get these tiny little voltage rises and this tiny little current flow that happens in the UHF, not RHF, radio frequency.
VHF, HF to VHF.
HF to VHF frequency range. And the TEV sensor can detect those signals. So what one of our engineers here, Thomas White, he's in the other office down there. Hi, Thomas. He's taking a TEV measurement on the front of this ring main unit here. So he's holding the instrument, the UltraTEV Plus2 instrument, on the outside of the switchgear, and that's how you take a TEV reading. The TEV, when you're running the test, what you can see on your screen is you will get a TEV magnitude, which is expressed in decibel millivolts. A lot of people just say decibels, but it is decibel millivolts. You'll also see another number, that's the discharge rate, and that's your pulse per cycle count, or your PPC count. And what that's telling you is how often per sine wave, per one cycle, that discharge is occurring in your top 10 decibels of your reading. Okay, and again, we've spoken a fair bit about getting a phase lock, but we've got written here, try and ensure a phase lock when recording data to capture it. Okay, so where to take TEV readings? So when you've got a switchboard such as this one in front of me, we would take a TEV reading on the outside of the circuit breaker, the bus bar chambers, the CT chambers, the VT, your cable termination box, and your cables. And when you're out at a transformer, do it at the cables and the termination box of the transformer. With modern switchgear, because modern switchgear is built like a whole bunch of big rectangular boxes, you can be quite limited to where you can test, but we tend to test at the front, the back, the top, and one of the best spots, if you take anything from what I'm talking about right now, is to take TEV measurements on the outside of your HV cables. So if you can get underneath a switchboard building and you can see all your HV cables, or your switchboard is up on stilts and you can see the HV cables, take TEV measurements on the cables, because quite often the decibel level and the pulse per cycle count and your phase plot that you capture at the cables can be higher at that point, even though the discharge is on the inside of the switchgear. And that's for a couple of reasons. The first reason is that your armoring and your screens on your HV cables act as a really good waveguide for your TEV signals to attenuate away from its source. And also because the TEV sensor, so the TEV sensor at the front of the UltraTEV Plus2 is physically only, a couple of millimeters away from those HV screens. It's just got to measure through the outside of your the thicker parts of the outside of the cable. Okay, so inside the UltraTEV Plus2, we've got a built-in guidance and interpretation graph. And to get to that, you go into TEV mode, and then there's a whole bunch of screens that you can click on, but one of them says interpretation. If you open up the interpretation screen, it'll show you what it's showing us here on the right-hand side of the screen. And it gives you what it's doing is it's looking at the decibel level and it's looking at the pulse per cycle count, and it's making a good rule of thumb judgment about what is most likely, the combination of that decibel level and that pulse per cycle count is. So it'll tell you most likely noise, or it'll tell you most likely high level internal void PD, or low level or medium level, or you may have an ultrasonic problem going on here, so check your ultrasonics. So that graph has been built up over time from many readings back in the past with the UltraTEV Plus1 instrument, because we couldn't see the phase plots then, and we didn't have the further diagnostic tools that we have now with the UltraTEV Plus2. So that interpretation guide is a good rule of thumb. It'll be right, a fair amount of the time, but it can also be wrong because of other factors such as noise coming onto the system. But in saying that, we have further diagnostic tools, which I'm going to go through now. Okay, so we've talked a lot about the phase resolved partial discharge patterns, or the phase plots, or the phase reference plots. That it all means the same thing. People just say different words to say the same thing. So here we have 4 examples of what sort of phase plots that you can detect with the UltraTEV Plus2. You can detect these with offline testing as well. It all goes into the same realm of analysing the phase plots. So the one in the top left there is a classic internal void single phase type discharge. If you guys are out there testing and you find that pattern while you're testing, you're very likely finding yourself an internal void problem somewhere near where you are testing, near where your TEV test is getting taken. The one underneath that, the one that says contact or floating metalwork type PD, that one there was actually captured from where we know there was a poor HV connection, and it was basically sparking and arcing and jumping across that gap and creating big TEV signals. And you can see there's a pattern there of 2 what we call rectangular looking clouds of events, and that there is a single phase contact type pattern. You can also get what's called floating metalwork type patterns, and that's where you've got pieces of metal close to HV that aren't necessarily earthed, or they aren't necessarily live, and they're not necessarily bonded, but they get an induced voltage on them because they're so close to the HV, and you get that a similar pattern to that. The one on the top right is we've found on a number of occasions partial discharge on the inside of an oil-filled transformer, and that's what the pattern we got for that. That's single phase. And then the bottom right-hand one is noise. So that's phase locked onto noise, and some sort of noise that would have been coming out of some sort of machine, or a variable speed drive, or electronics, or whatever. You can get many different types of noise. That's just an example. All right, so internal void. So what we have here is a CT that's blown up in service. These types of CTs are renowned for having a gap, a physical gap inside them from when they were first built. And the cast resin was poured into the mold, and they left an air bubble in there, or multiple air bubbles. It doesn't really matter. But what tends to happen is they give out big TEV signals, and internal void type TEV signals, and you will see what the pattern looks like on the left there. They give out very high level TEV signals, and that's just a bit of a case study on that.
Yeah, the main thing on this particular one is if we see that specific pattern on that type of switchgear, we know almost certainly that it's coming from that component. The more that we can develop these databases, so we can keep taking these readings and correlating the actual findings with where the pattern shows, the more that we can do that. So we have an absolute level of certainty on that type of switchgear. When we see that specific type of pattern, we know exactly which components it's coming from. The more we can do that, the better.
Yeah, so a lot of this stuff comes down to engineering judgment and history of failure, which we'll talk about soon. Okay, so where are the signals coming from? So another big point that you need to take from these slides is that TEV signals will travel. They will be, if you've got a defect, the defect is discharging, it's releasing the UHF signals they radiate away from the source, and they travel away from the source. They can travel through the air, but they mainly travel through anything that's conductive. So they'll travel through the cores, they'll travel through the screens, they'll travel through the switchgear, and radiate away from themselves. So what you can see here on the right-hand side is a survey that's been taken with the UltraTEV Plus2. The UltraTEV Plus2 will grade all the different decibel levels into green, amber, and red. And you could show that pattern or that picture to an uneducated person, and they'll go, "Oh, there's most likely a problem there where your red signals are," and that's right. That everything's irradiating away from that point. Now these are all readings that have been taken on a switchboard. Just because we've got the highest readings on that last panel on the switchboard there, it doesn't necessarily mean that the defect is on the inside of those chambers there. That'll be getting fed by a HV cable. The problem could be at the far end of those cables, and the TEV signals could be getting imported from whatever's at the other end, or it could be getting imported from cable PD within the cable itself. A lot of time cable PD occurs inside joints because of water ingress over time, or manufacturing or workmanship sort of defects in the joints. So what we can do to help figure out where it's coming from is use what's called the time of flight TEV technique. Well, I'll go through that in a sec. Okay, so here's a case study of how a discharge source was diagnosed. What you can see on the right-hand side there is TEV levels that were recorded over 1 week by a 24/7 PD monitor at a particular switchboard. You can see at the start of the week that there were no signals, and then signals jumped up to a level of around 35,000 pulses over time. It's just looking at pulses there, but it was on for a few days, and then it turned off for a section of a day, and then it turned on again, and it stayed on. So at the end of the week, we analysed all that data and said, well, there's something going on either in this chamber or near this chamber, and we know that when, for some reason, the signals went away. So we looked back at the switching history, and we found that the breaker was open when we installed the monitor, then they closed it, and then they opened it again for a certain amount of time, and then they closed it, making certain that the TEV signals came and they went, and they came and they went, okay, over time. So the next step in diagnosing was, okay, we've got discharge, we're detecting it by a TEV, let's go out there with an UltraTEV locator. So the instrument you can see there, that red instrument there, is called an UltraTEV Plus2 locator. That there will plug into your UltraTEV Plus2 instrument. And what it does is whenever I or Neil or anyone in this office finds a TEV signal of concern, you want to track down where it's coming from. So we always take a locator with us wherever we're testing. And what we do with the locator is we're able to basically put 2 TEV sensors onto the outside of switchgear or onto the outside of cables and figure out where the signals are coming from. Sometimes it's not where the highest signals are. There's been many case studies where we've found where it's not necessarily where the highest are. So what we did in this one, here's your pen. What we did in this one is we found that at that circuit breaker, the switchboard down the bottom, switch room down the bottom of the, what's that called, that diagram, is where the UltraTEV monitor was monitoring for a week. When we came along with the UltraTEV instrument, the Plus2 instrument, we measured 26 decibels on the board and then 28 decibels on the cable, but we were able to use the locator, and the locator was telling us that the signals aren't coming from inside the switch room, they're coming from somewhere else. So we went to the far end of that cable, which was 10 meters away. We were measuring 30 on the switchgear, 25 on the cable, but it was telling us, again, it's coming from down the circuit somewhere. So then we tested that switchgear. We went to the next cable along, and it was 25 and 30. Again, it was saying away from here. And eventually, the locator took us all the way out to transformer number 47, where it says T47, where there's a level of 42 decibels there. And that's where the locator took us to, and that was the, that was the source of where the PD signals were coming from. We looked at the history of that cable box that feeds that transformer, and that had a failure there maybe, I don't know, 6 months or a year before. They'd shut it, the failure itself caused the shutdown, but they did a quick fix inside that cable box. They fixed it up, they bolted it all back together, and they got it up and running again to help get production back on. But in doing that quick fix, they'd caused another PD defect that would have failed eventually over time. So now that we've found and located all the way through to transformer number 47, we can, the client can manage that through to whenever the next shutdown will happen and plan for the next shutdown and get in there and fix it properly, because that cable box will eventually blow up again at some stage. Okay, so what do the numbers mean? So this is where we talk about the decibel level. So in the past, EA Technology have created a big, large database of all the TEV signals that have ever been taken, and they've classed them into decibel levels. So, and they created a cumulative probability curve. So that's that curve you can see on the left-hand side there. So the curve's telling us that the bottom 75% of readings are going to be 20 decibels or less, and that's why they get classed as green, and that's why your instrument says that they're green. The next 15% of readings that are taken are between 20 and 28 decibel levels, and that's amber. And then your top 10% will be 29 decibels and above turns into red. Now, so when you find a high level signal, that is unusual to find that. Like, you know, I've been out and I've taken, you know, hundreds, if not thousands of readings, and most of the time you're getting very low readings, low, 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 low. And then when you get these medium ones and these high ones, you have to figure out what's going on, what's causing them, and is it unusual? And the answer is yes, it is unusual. So we use the amplitude, and then we use the interpretation graph, which is built into the instruments anyway, where we look at the decibel count, the pulse per cycle count, and the instrument will give us a good rule of thumb as to what it most likely is, and that's based on past past experience of diagnosing defects. But then now with the UltraTEV Plus2, we've got the phase resolve patterns, and we've also got another function in there with the waveforms. So the graph on the top right is a phase resolve pattern. We can look at those patterns and we can say whether it's PD, we can say whether it's single phase, two phase, three phase, internal void, whether you've got a contact issue, whether you've got a floating metalwork type issue, whether you've got a corona issue, a surface issue, all that type of stuff, and we can use that to get a very good information about exactly what's going on. We can also use the waveforms at times to analyze what's going on and looking at how sharp things are and all that sort of stuff. Is there anything you want to say on that?
No.
Cool. So here's a case study that I'll quickly go through with all you guys. So this was one of my ones where I was out testing, and I found that the switchboard itself was very, very noisy in terms of TEV, so very electrically noisy. So here we have a switchboard, or J18 switchgear, air insulated bus, oil-filled breakers, probably built around the 1970s, that type of thing. Scanned the whole switchboard, and this is what I got. I got very high levels across the whole switchboard. So wherever you've got a red reading there, that's 30 decibels or above worth of TEV. Now, when I look at that, I think it's very, very noisy. You've got imported noise coming from somewhere, because it's super unlikely that all of those chambers are discharging, because you'd have explosions left, right, and center. It just wouldn't be occurring. So this next slide is a typical example of what I was finding. So this pattern here, where you can see these big rectangular boxes, these sharp lines of events. This was a level of 36 decibels and 8.75 pulses per cycle. Is all that stuff is indicative of, how I said before, contact or floating metalwork type issues. You can see the TEV interpretation on the left-hand side there, in this case, is correct. It's saying likely floating metalwork or poor connections, and that's just based on the decibel level and the pulse per cycle count. But I can also look at that picture and say to myself, well, that's imported signals. Those signals aren't coming from inside the switchboard, because I can see them on the whole switchboard, basically. Now, we went outside and did a scan outside, and we found that there was a 66 kV air brake switch. This was one that Neil found a little bit earlier than before I got there. But this 66 kV air brake switch, which you can see on the left, had some sort of poor connection up the top there, or some sort of floating metalwork type issue where you've got a piece of metal that's just not bonded together properly or close to the HV, and it's causing discharge. So it was causing, you can see again that big long rectangular pattern. It's actually 50 decibels out in the yard, whereas on the switchboard it was, as I said, 36 decibels in a lot of spots. And then that center graph there is what the PD Hawk captured. We're not talking about the PD Hawk much in this, but we did use the PD Hawk, and we were able to isolate the signals coming from there. Well, Neil was anyway when he was down there. But so when all that noise was there, I was able to use the phase resolve partial discharge patterns to diagnose an actual internal void type defect. You can see on the right hand side here where I've drawn those red lines above those patterns of events there, where you've got these two waves of activity, which is indicative of internal void type PD from the earlier phase plots that we were looking at. You can still see all this other noise, you can still see the contact type issues coming through, but you can see at the same time the internal void. So then what did I do? I got the UltraTEV locator out, and I was able to test the cable, and the cable was telling me that the PD signals weren't coming from inside the switchboard, they were coming from somewhere else. So what did I do? I walked to the other end of the cable. The other end of the cable was in the main transformer of the zone substation. So the cable in question was that one there that I've circled in red, where it goes under the ground, it's probably 20 meters long to the switchboard, comes up and it terminates itself inside that cable box there. And in there, I found levels of 36 decibels and 0.76 pulses per cycle. But I found the exact same pattern. I also was able to get the UltraTEV locator out and use the locator. I tested between all of those cables there. There's actually 6 cables going into that box. I was able to go red to red, red to white, red to blue, and also up into the cable box and find a direction. And the locator told me that the signals were emanating inside the cable box on one particular cable out of all 6 cables. And at that point, we've diagnosed where it's coming from. The most likely cause of it is a termination defect, like a workmanship defect in the termination. And that is how we diagnose that one. We're able to work with the customer on that one we've monitored that over time. We actually installed 24/7 monitoring sensors out at that cable box, and we've monitored it over time and tracked it. And what the customer was able to do then was bump that up the list of things that they need to fix on their network. So they're actually replacing that indoor board, and at the same time during that same project they're going to replace all of those transformer cables that feed that transformer. So they're going to get that defect off their network. Okay, so interpretation of TEV results. The absolute number and the trending is useful and is always considered for TEV. So what that means is over time, TEV signals tend to get worse as they go towards failure, as opposed to what Neil said earlier, where ultrasonic amplitude levels don't necessarily get worse before failure. The pattern will always help you diagnose the type of defect, and it will provide additional certainty. With the older instrument, the UltraTEV Plus2, all you had to go on was the decibel level and the pulse per cycle count. Now you've got the decibel level, the pulse per cycle count, the phase resolve patterns, what the instrument thinks it is, and the waveforms to help you diagnose what's going on. Okay, the highest TEV amplitudes will not always be where the source of activity is, and that's where the UltraTEV locator comes into its own, and it helps you track down where the signal's coming from. A visual examination may not help, as the defect is often internal to the insulation. So if you see that asset there on the right hand side that's been cut into 4 pieces, if that wasn't cut into 4 pieces, the outside of that asset there would look completely fine, even though there's discharge on the inside of it. So it's important to realise when you're getting TEV signals and you've diagnosed it down to a certain asset, or the most likely certain asset, you open it up for an inspection. There's pretty high chance you won't see anything. Okay, and then consider your failure history. So when you are looking at what your decibel levels are, your pulse per cycle count, your phase resolve pattern, and you're putting all that together, you've also got to remember what you're testing and where the test is being taken. So if you have an asset, just say you have 100 of the same type of switchgear out on your network, and you're continually having a bus bar failure inside that asset, and you go out and test them all, and you're getting levels of 20 decibels at the same spot on certain ring main units, that 20 decibels may be the critical level just before it blows up, even though on our interpretation it's not the highest thing, it's not the highest number. So considering the failure history, we also have different defects that can be quite, sort of high in amplitude, but they can take the PD for a fairly long time. So you end up with discharge sitting there for a while. But that also helps you diagnose what the problems are as well. So there's a fair bit to it. Okay, so Neil is going to run through our summary.
So, all right, we'll do another swap over.
Just in case there's questions.
Okay, so you found PD, and you may not be able to get to it quickly. The simplest way of preventing failure, of course, is to take it off the system. So if you can get in there and you can fix it up, we've had questions about how long and stuff like that. It's a difficult question. Ultimately, you've got PD on the system. It will eventually degrade and it will eventually cause failures. The quicker you get it out, the better. You've got some countries that concentrate on getting everything away. So they're looking at, they won't tolerate low levels of discharge. We've shown examples and case studies where You know, you can have discharge that lasts for a number of years. Eventually, you're going to have to take it off. And then you've got the whole situation when you're in an industrial site or even on an electricity network where, when can I take it off in a controlled manner? Before you do that, then there are a number of things that we suggest that you can do. So isolate the suspected circuits if possible. So if you've got one particular circuit breaker, that the one that we saw T47, T48, can we just use T48 for a while? Take that T47 off the system. The answer was no in that particular case. So what we then did is continue to monitor until the outage was available during the shutdown. If it's a surface PD problem, we've shown that the number is not necessarily an indicator of how close you are to failure. But what we've also shown is the difference in the level of degradation or the amount of discharge that you can get based on the amount of humidity in the atmosphere. So 75 times higher for a very humid place. So if you've got surface PD and you're trying to slow that degradation and further deterioration down, control the environment, look at the air conditioning, bring the humidity down, and you can do that, and that will buy you a certain amount of time as you're planning for changing on that. Keep the system stable, reduce the switching. You've got situations where if you switch something out to visually examine for, say, surface tracking, switching it back in is your critical time. So when we showed that picture and there was only 2 or 3, 4 millimeters of insulation left, that specific time we switched that out in the lab, and that was fine. We switched it out, we took all the photographs. As soon as we switched that back in, it disruptively failed. So that's a critical time. So if you are taking things out or you're doing switching is a critical time. So if you can reduce the amount of switching, if you take it out, be careful about putting it back in, particularly with surface type tracking. You've got, it's still a relatively low probability of a failure happening when you're in the substation, but it's a higher probability. So for a safety aspect, limit the access to the substation or the time spent near the suspect asset behind the switchboard, things like that. And of course, what we've done in many times and what people do is install monitoring so you can monitor it through there to see if anything is accelerating away and making changes. As we've said, ultrasonically, that may not always be the best issue, but if you're trying to control the environment, you control and monitor the environment and you see how much discharge is taking place. So they're all the things that we would suggest are put in place until you can ultimately take it off the system and fix it up. If we do all that, then we should be able to achieve our objectives for that: improved asset performance, greater reliability and safety, and lower costs. The smarter investment decisions is really using partial discharge as a tool for what do I need to take off my system first, not just using age, and that comes into the whole condition-based and risk management of network assets. And Brad is busily typing away. We're happy to take questions, additional questions now. We're also happy to take additional questions as we go on. Those of you who've got UltraTEV pluses or our instruments, and you want to know exactly what the readings are meaning, then we're quite happy to take that. We've got people here, and we've got lots of people up in Southeast Asia. Hello to all you guys. So you can always book or ask the Singapore office as well for advice on that. So we're here to help, basically. So any questions now or any questions in the future, feel free to reach out and contact us. Any more from you, Brad? Anything happening? Any further comments? We got
condition when we have a
all right, we had a question about the histograms. The histogram tab on the UltraTEV Plus, we don't use that hugely amount, really. You're going to get the same information about histograms as you do on the PRPD. So what the histogram really is there to show you is is how many clusters, how many different sources of PD that we've got. So it's almost that used in conjunction with the PRPD. It also allows you to see the number of pulses per cycle associated with the different clustering as well. So we do use it when we've got a very complicated PRPD pattern. We will open the histogram up, and we will look underneath that to see what the pulses per cycle are in the different clusters. So that's where we tend to use the histogram. PRPD is generally the most one that we use. Yeah, we've done. All right, LED lighting in the substation. We have posted a comment on that. LED lighting, great for reducing the bills, terrible for giving you a phase lock. So on a phase lock, some LED lighting does work. You can try the EMF type or phase locking device in the system, but generally you have to go for for using the manual mode, and I think we answered that in some of the questions earlier.
Well, I think that's it. I don't think Stanley's just put that up. Yeah, so Stanley's saying that they found with our PD testing program on 11 kV cable terminations, we've been successful in finding quite a few cases that would have catastrophically failed if left unattended. Just sharing the success story. Yeah, so that's what it's all about. Excellent. That's good.
Yeah,
very good.
We had a good one. We had a guy phoning up the other day and saying how much they've saved in terms of millions from outages in using the PD tester, and he's still using an UltraTEV Plus Smart 1. I think the amount of money he's saved by now, he should have bought +2, but there we go.
Okay, so we've got a few more questions coming in, but probably I don't know if they'll.
Okay, so right. So we've mentioned previously the measure on the cables and cable basement. Does that mean we directly place the TEV on the power cable or use HFCT? Yes and yes. So always measure on the cables. If there's one good bit of advice, if you can see the cables on the switchgear, take a measurement there. It's really, really useful. So the one where we trace it all the way back to that transformer T47, all of those readings taken without access to using HFCT on the earth, because it's a plumb joint at that point. If you've got multiple earths and a plumb joint, you're not going to get access to the HFCT or to use HFCT. If you do get an insulated cable gland that can use that, that's additional information. We're likely to do the next webinar is going to be on the topic, and we're going to start introducing the additional technologies for the HFCTs, UHF, and why and where we use those sort of things as well. So that's useful to people.
Would the phase resolve partial discharge pattern of the TEV and the HFCT on cables be similar? The answer is yes to that. So if you just get out the UltraTEV Plus2 and take a HFCT reading, you'll see the output of that. It comes out the same as the TEV. It's just a TEV is all positive, but the HFCT will show you negative and positive. It comes out in picocolumns and pulses per cycle, as opposed to decibels and pulses per cycle. But that's the answer to that one, Edson.
Yeah, the patterns are the same. It's quite interesting. Sometimes you'll find, even so, we saw Brad showed the one with the 66 kV yard where we had the air brake switch with the flat lines. You can at times see that impinging onto the cables. So the signals couple, and they couple very well, which is where we use the locators to start narrowing where things are coming down from. So you can sometimes see that sort of contact noise then impinging onto the cables and found on the cable earth screen. So do have to be relatively careful on that as well, is that you can find something on a cable earth that is actually coming from a different asset, which is outside of what you're specifically trying to test. And cable to cable will also couple, but that's a topic for another webinar, I think. Getting there, Brad?
Yeah, I've finished. I'm just answering.
Well, we want one more answer. So thanks very much for attending. We've got our contact details up there. If you want to reach out to us, we're more than happy to do that.
Training.
we will be running a training, a larger training, online training course as well. So we'll be in touch with information about that coming forward, and we'll also be in touch with information about the next topic of webinar that we're going to be pushing out there as well. So thanks very much for everybody attending.
Just one last question.
One last question.
Is the measurements the same to SF6 equipment insulation from air? Right.
Yeah. Generally, the answer is yes. You're going to get less. There is less potential of getting surface type tracking or corona in particular on SF6 instruments. Ultrasonic, if you're measuring SF6 filled equipment and you're measuring ultrasonically, you're not realistically going to get anything. Otherwise, you've got a bigger problem where your SF6 has gone out because you've got no air gap. You very rarely get much picked up with a contact probe either. The transient earth voltage becomes a significant tester there. So we have found problems in SF6 equipment. TEV becomes the primary tool because you get much less in the way of surface discharge occurring. So yeah, new SF6 equipment, old compound insulated equipment, and everything in between, we test and successfully find problems.
That's it. Everyone's just saying goodbye now.
Okay.
Thanks everyone for joining in.
And see you again.
See you on the next one.
Yes.